So the first couple problems we're going to work on today are from the rotational kinematic motion chapter. So example 1 says that the drive propeller of a ship starts from rest. Right, so an initial angular velocity of 0 radians per second. Right, starts from rest and accelerates at 2.9 times 10 to the negative 3 radians per second squared. To the negative 3 radians per second squared, or 2.1 times 10 to the 3 seconds. Or 2.1 is 10 to the 3 seconds. So basically 2,100 seconds, however long that is. So for the next 1.4 times 10 to the 3 seconds, for the next 0.4 times 10 to the 3 seconds, right, the propeller rotates at a constant angular speed. The propeller rotates at a constant angular speed. Constant angular speed. So the problem goes on to say, then it decelerates. At 2.3. 10 to the negative 3 radians per second squared. Until it slows without reversing. Until it slows, right, without reversing direction. To an angular speed of 4 radians per second. An angular speed of 4 radians per second. So the problem wants us to find the total angular displacement of the propeller. Find the total angular displacement of their propeller. Right, so it's example 1. So this problem is broken up into 3 parts, right? The first part, so part 1 is a constant acceleration problem. Right, part 2 is where now it's going at a constant angular velocity. Constant angular velocity. 3 goes back to constant acceleration again. And when I say acceleration, I actually mean angular acceleration. Although the ship itself should also be accelerating during this point. So then the total displacement is going to be given by the displacement from part 1 plus the displacement from part 2 plus the displacement from part 3, right? So basically how much it turns in part 1, part 2, and part 3 all added together. So let's look at part 1. So for part 1, right, we're starting from rest. So our initial angular velocity is 0 radians per second. The problem tells us that our angular acceleration, call it A1 or alpha 1, is going to be 2.9 times 10 to the negative 3 radians per second squared. And then it does, like, it accelerates like this. It angularly accelerates like this for 2.1 times 10 to the 3 seconds. Right, so we want to find basically how much the propeller has turned during that time. So we know that our angular displacement is equal to our initial angular velocity times time plus 1/2 times our angular acceleration times time squared. But since our initial angular velocity is 0, right, this first term is gone. And so the initial angular displacement for the first part of our problem is just 1/2 times our angular acceleration, 2.9 times 10 to the negative 3 radians per second squared, times the time squared. So 1 times 10 to the 3 seconds, squaring that. This is going to give us, so the angular displacement for the first part of our problem is 6.39 times 10 to the 3 radians. All right, that's how much it turned in the first part of the problem. So for part 2, right, now we're going at a constant angular velocity, but we need to figure out what that constant angular velocity is. So for part 2, the angular acceleration, I'll say for part 2 that angular acceleration is 0. W is just a constant, or omega is just a constant. So we need to find how fast this thing is rotating. But how fast it's rotating is given by the final angular velocity of part 1. Okay. So the final angular velocity of part 1 is just equal to the initial angular velocity of this thing plus how fast it was accelerating in part 1 times how long it was accelerating like that for, right? So the initial angular velocity was 0 per second plus our angular acceleration of 2.9 times 10 to the negative 3 radians per second squared times how long we're accelerating like that for. So that's going to be 2.1 times 10 to the 3 seconds. So putting all that all together, we get, right, the angular velocity of our propeller at the start of part 2 is going to be 6.09 radians per second. Right. And so because there's 0 acceleration, or angular acceleration for the second part, our angular displacement for the second part of the problem is just our angular velocity times how long we're going on like that for. So in this case, right, this is our angular velocity of 6.09 radians per second. And apparently we're carrying on like this for the second part of the problem. It says 1.4 times 10 to the 3 seconds. So 1.4 times 10 to the 3 seconds. Right, this is going to give us an angular displacement for the second half of the problem of 8.53 times 10 to the 3 radians. 8.53 times 10 to the 3 radians. So that's how much it's turned in the second part of the problem. And last but not least, part 3. Well, now we're slowing down. So our angular acceleration for part 3 is going to be minus 2.3 is 10 to the negative 3 radians per second squared. And the initial angular velocity for this part of the problem is just the angular velocity that we found in part 2. Right, so that's going to be 6.09 radians per second. Radians per second. And so the final angular velocity of this part, the problem tells us, is just 4 radians per second. So if we're going to try and find the angular displacement for part 3, we know that the final angular velocity squared minus the initial angular velocity squared is equal to 2 times our angular acceleration times our angular displacement for part 3, right? So if I divide both sides by 2 times our angular acceleration alpha, we get that our angular displacement for part 3, right, is just our final angular velocity squared, which is 4 radians per second. It's 4 radians per second. I'm going to square that minus our initial angular velocity, which was 6.09 radians per second. We're going to square all that. We're dividing all this by 2 times our angular acceleration for this part, which is minus 2.3 times 10 to the negative 3 radians per second squared. Right. When you punch all this in, we get, for the third part of our problem, we get an angular displacement of 4.58 times 10 to the 3 radians. Right. And so now we have the angular displacements for each part of the problem. Right, and to find the total angular displacement, we just have to add everything up. Right, so that's the total angular displacement of this propeller over the course of this little adventure. Just all of them added together. Right, which in this case is 19.5. Right, times 10 to the 3 radians. So that's the total angular displacement of this propeller. And so that's the end of problem 1. All right, so problem 2 is also from the rotational kinematic motion chapter. This is example 2. Example 2. And example 2 says, an auto race is held on a circular track. So an auto race is held on a circular track. So the problem goes on to say that a car completes 1 lap. A car completes 1 lap in a time of 18.9 seconds. Time 18.9 seconds, right? With an average tangential speed. With an average tangential speed. Right, so generally what it would show on the speedometer of the car of 42.6 meters per second. Meters per second, right? So this problem wants us to find, for part A, wants us to find the average angular speed average angular speed as well as the radius of the track. So this problem's not too bad, right? So for part A, right, the average angular speed, just omega, right? That's the change in our angle or our angular displacement divided by the elapsed time. So this car makes 1 lap around the track, so 1 lap. The angular displacement of 1 lap is just 2 times pi radians, right? And it does this in a time of 18.9 seconds. So this gives us an average angular velocity of 0.33 radians per second. So that's part A. So 1-line solution. And part B is asking about the radius of the track. But we know that the tangential speed is equal to the angular speed by this radius r. So we just found the average angular speed of this track, right? So if we divide both sides by omega, we get that the radius of the track is equal to the tangential speed divided by the angular speed. So in this case, the problem tells us that the tangential speed is 42.6 meters per second. And the angular speed we found to be 0.33 radians per second. So this gives us the radius of the track to be 129.1 meters. All right, and so that's it for the rotational kinematic motion stuff. So the next section we're going to work on are problems from the rotational dynamics section. So this is going to be rotational dynamics problems. Right. So now we're going to be looking at example 3. So example 3 says that a hiker who weighs 985 newtons, is strolling through the woods and crosses a small horizontal bridge and crosses a small horizontal bridge. The problem goes on to say that the bridge is uniform. The bridge is uniform. It weighs 3,610 newtons. So it weighs 3,610 newtons and rests on 2 concrete supports at each end. And rests on 2 concrete supports at each end of the bridge. So the problem goes on to say that the hiker stops 1/5 of the way along the bridge. Hiker stops 1/5 of the way across the bridge. So the problem's asking, what is the magnitude of the force? So what is the magnitude of the force that a concrete support exerts on the bridge? That a concrete support exerts on the bridge. So at the near end, and I'll draw a picture. And part B, the far end. Okay. So the associated picture is we've got a bridge, which looks like this. There we go. And this is being supported by two concrete pillars, one at each end. So concrete pillar here, concrete pillar here. Right, and then there's just some schmuck, which is walking along this bridge in the woods. And this person has some amount of weight. So let's just pretend that all the weight from this person is being exerted here. So this is the weight of the person. Call it WP. And at each end of this bridge, right, there's going to be the normal force of these concrete poles pushing up. Call it Fn1, Fn2. Right, these are the normal forces of the concrete poles pushing up on the ends of the bridge. Right. And something that I didn't cover when I was talking about the center of gravity, if you have an object that's highly symmetric, like this bridge, and it's uniform, then the center of gravity is going to be at the very center of that object. So in this case, the weight of the bridge can be considered to be acting entirely at this point right here. So this is the weight of the bridge. So the problem goes on to say that the distance between one end of the bridge, right, and where the hiker is 1/5 of the distance of the bridge. So this is some distance L over 5, right, where the total distance, the total length of this bridge, we're going to call it L. Okay. So to begin with, we need to find the normal force on the left end of the bridge. So what I'm going to do, I'm going to place our axis of rotation right here at the center of gravity of this bridge. So this is going to be our axis of rotation. Right. So let me zoom out a little bit. Maybe not that much. Okay, so to begin with, we're solving for part A. What we need to do is, this is an equilibrium problem. So what that means is the sum of the forces in the x direction are 0, the sum of the forces in the y direction are 0. And then when we add up all the torques in this problem, those should also be 0. So to start with, we're going to look at the sum of the forces in the x direction. Right? But if you notice, there are no forces in the x direction, right? They're all in the y direction, so this is useless here. but we can look at forces in the y direction. Right, and we don't want this bridge lifting up into the, the atmosphere. We also don't want it sinking into the ground. It would be kind of a bad bridge if it did that. So we want the acceleration of this bridge to be 0 in the y direction. Okay. But the sum of the forces in the y direction are, we have this normal force and this normal force pointing upwards. F1 plus N2, right? And then we have the weight of the person and the weight of the bridge pointing down. So it's going to be minus weight of the person minus weight of the bridge. And all that's equal to 0. So I forgot that the problem tells us that the weight of the person is, 985 newtons. And that the weight of the bridge is 3,610 newtons. So I forgot that we had both had those pieces of information, but I'm still choosing to put the axis of rotation here because it makes the problem a little bit easier. So I'm going to say that this is our equation 1. So this is equation 1. And if we look at the sum of the torques in the problem, right, we want those to be equal to 0. So looking at our drawing here, remember, any force that makes this bridge go counterclockwise is a positive torque, and anything that makes it go clockwise is a negative torque. So looking at this, right, if we're looking at force F1, so if we pretend all these other forces aren't here, and this normal force is the only force acting on the bridge, right, this is going to make our bridge go clockwise around our axis of rotation. So that's going to be a negative torque, so it's going to be minus the magnitude of this normal force times the distance away from the axis of rotation we are. So I should probably mention that it's kind of running out of room to draw stuff, but the distance between one end of the bridge and our center of gravity, right, this is just L over 2, right, it's halfway in the middle. So it's just L over 2. And then we have the weight of the person, right? So this is going to produce a counterclockwise rotation in the bridge around our axis of rotation. So this is going to be plus the weight of the person times their distance away from, the center of the bridge. But their distance away from the center of the bridge is just this distance right here, but that's just L over 2 minus L over 5. And additionally, we don't have to worry about the torque caused by the weight of the bridge because the distance between our axis of rotation and the weight of the bridge, right, that distance is 0, so therefore it produces no torque. And so last but not least, the last torque that we have to consider is the torque produced by this second normal force. So in this case, this is going to make our bridge go counterclockwise again, so that's a positive torque. So that's going to be, maybe I should move this down. So plus the normal force exerted by the far end concrete post times its distance away from our axis of rotation. And all that should be equal to 0. 0 Newton meters. So notice how L appears in every single term on the left-hand side. So if we divide both sides by L, then we can get rid of all these L's on the left-hand side. And if we divide 0 by L, well, that's no great loss because 0 divided by pretty much anything other than 0 will still be 0. So as a result, all this boils down to the normal force of the far end concrete pole pushing up minus the normal force of the closer concrete pole plus the weight of the person. And here we have 1/2 minus 1/5 that's going to be equal to 3/5 or 0.6. Okay, and all this is equal to 0 newtons. So this is going to be our second equation. Equation 2. Right, where this 0.6 literally came from taking 1/2 and subtracting 1/5 off from it. So now what we can do, we can solve equation 1, right? We know what the weights are for the person in the bridge. So I'm going to add both of these to both sides. So from equation 1, right, we have the normal force exerted by the first post plus the normal force exerted by the second post. It's going to be equal to the weight of the person plus the weight of the bridge, right? Where the weight of the person was 985 newtons. The weight of the bridge was 3,610 newtons. Right. So what we know is that the normal force of the first post plus the second post, right, that has to be equal to 4,595. 4,595 newtons. Right. And then from the second equation that we pulled out, right, I'm going to basically subtract this off from both sides to get the normal force of the second beam minus the normal force of the first beam. And that's going to be equal to minus the weight of the person. So that's 985 newtons, right, multiplied by 0.6. So in this case, we have the normal force F2 minus the normal force Fn1. That's going to be equal to minus 591 newtons. Right. So now look what happens if we take this equation and we add it to this equation. Right, we add both the left sides together, and then that's going to equal to both of the right sides added together. So notice that we have this plus this. So the normal force from our far end ends up adding together, right? But we have the normal force from our first post minus the normal force from our first post. So those cancel out. So this becomes 2 times the normal force for the second post. It's going to be equal to this plus this, 4,595 newtons minus 591 newtons. So that's going to be equal to, right, 4,004 newtons, right? And on the left-hand side, we have 2 times the magnitude for the normal force on the far end thing. So, you know, we're kind of doing part B first, but we're going to sort of solve these simultaneously. So if I divide both sides by 2, we get that the normal force exerted by the concrete post on the bridge is 2,002 newtons. Right, so that's one of our answers. In fact, this is the answer to part B. Right. So part B's answer. Right. And then if I just multiply this equation by -1, right, this becomes Fn1 minus Fn2. And then on the right-hand side, since we multiply by -1, that's just 591 newtons. And then we're going to do the same thing. We're going to take this equation, we're going to add it to this equation up here, right? So in this case, the normal forces from the first post add up, and the normal forces from the second post end up canceling out. So this becomes 2 times the normal force from the first post. It's going to be equal to 4,595 newtons, right, plus 591 newtons. So that's going to be equal to 5,186 newtons, right? And now if I divide both sides by 2, we get that the normal force exerted by the first post, like the one closer to the hiker, this ends up being equal to 2,593 newtons. So 2,593 newtons. So this is the answer to part A. So part A's answer. All right, so with that, we finished the problem. So let's move on to example 4. Example 4. So example 4 says that a bowling ball encounters a 0.76 meter vertical rise. So encounters a 0.76 meter vertical rise, and I'll draw a picture associated with this. So it encounters this vertical rise on the way back to the bowling ball rack. Yes. On the way back to the ball rack. So ignore frictional losses and assume that the mass of the ball is distributed uniformly. So ignore frictional losses. So basically pretend like friction isn't a thing here. And assume that the mass of the ball is distributed uniformly. And assume that the mass of the ball is distributed uniformly. Right, so this is saying like, you know, the ball is uniformly distributed, right? It's not like all the mass is in the center of the ball and like there's less mass as you get to the edge. It's all, if you were to take any sort of slice from it, it would have the same, you know, density. So the problem goes on to say that the translational speed of the ball, the translational speed of the ball is 3.5 meters per second. It's 3.5 meters per second at the bottom of the rise. At the bottom of the rise. So find the translational speed of the ball at the top. Find the translational speed at the top. At the top. All right. All right, so let me draw a picture associated with this problem. So we have something like this, and then we have the bowling ball rise. So it starts with like this, and it goes up like that. Right, and then at the bottom here, got our bowling ball. Then it goes up the rise, so it reaches the top. So we have our bowling balls, right? The distance between the bottom of the rise and the top of the rise, this distance here is 0.76 meters, right? So the ball's rolling. Ball's rolling. So the problem tells us that at the bottom, right, this bowling ball is moving at 3.5 meters per second. And then we're tasked with finding the velocity of the ball right at the top. So one thing that we're going to need in order to solve this is we need to know the moment of inertia for a sphere, and bowling balls are spheres. So the moment of inertia for a sphere is 2/5 times the mass of the bowling ball times the radius of the bowling ball squared. Right, that's the moment of inertia for this bowling ball. So what we're going to do, we're going to use conservation of energy to try and solve this problem. So I'm going to say that the height here at the bottom of the rise is 0, which means that the height here at the top is that 0.76 meters. So we're going to start by writing down our total initial energy. Right, so it's going to be our initial kinetic energy, 1/2 mv0 squared, plus our initial kinetic energy, which is 1/2 I omega squared, right, plus our initial gravitational potential energy. But because we're starting at the bottom at a height of 0, right, that means that this term is gone. So our total initial energy is just 1/2 mv0 squared plus 1/2 times I omega naught squared. Right? But we need to figure out what our initial angular velocity is. But we know that the relationship between our linear velocity for our ball and the rotational angular velocity is this relation right here. So we can solve this for omega naught, our initial angular velocity, right? That's just our linear speed divided by the radius of the bowling ball. And so if we take the moment of inertia of our sphere, plug it in here, and we take the initial angular velocity and we plug it in here, we get that the total initial energy for our bowling ball when it's at the bottom of this little slope here, it's going to be equal to 1/2 mv0 squared. All right, we're not going to touch that, plus 1/2 times the moment of inertia for our bowling ball. So that's 2/5 times the mass of the bowling ball times the radius of the bowling ball squared. And then we're going to multiply that by omega naught squared, but omega naught is just v naught over r. So we square that to get v naught squared over r squared. And these r squareds cancel out, luckily enough. And this 1/2 is going to cancel with this 2 up here. So then the total initial energy of our system is just 1/2 mv0 squared plus 1/5 mv0 squared, right? And so we can factor this mv0 squared out of both. This becomes 1/2 plus 1/5 times mv0 squared. But we can rewrite 1/2 as 5/10. And we can rewrite 1/5, right? If we multiply the top and the bottom by 2, this gives us 2/10 right, times mv0 squared. So this is just 7 divided by 10 times mv0 squared. And at the moment, that's all we can do. So this right here is the initial energy of our bowling ball when it's at the bottom of the ramp. And now let's look at the total energy of our bowling ball at the top of the ramp. All right, so that's equal to 1/2 mv squared plus 1/2 I omega squared, right? That's our final rotational kinetic energy, plus mg hf. So this is going to be pretty much the same, right? Because this part hasn't really changed, right? If we do the same process that we did in this first part, right? We treat our final velocity, right, in terms of our angular velocity, right? So we solve for omega. That's going to be our final velocity divided by r, right? And then we basically do the same thing that we did in the first part here, where we plugged in, the moment of inertia. We plug that in here, plug this in for here, and this is going to give us a final total energy of 7 divided by 10 times the mass of the bowling ball times the final velocity of the bowling ball squared. But then we still have this extra gravitational potential energy term, so that's plus mgh f, right? And this is going to be our final total energy. So because of conservation of energy here, we say that this is going to be equal to this. So on the left-hand side, we have 7/10, right, 7/10, times the mass of the bowling ball, times the initial velocity of the bowling ball squared. And on the right, we have 7/10 times the mass of the bowling ball, times the final velocity of the bowling ball squared, plus mg times the final height of our bowling ball. But notice that the mass of the bowling ball is on both sides of this equation, right? It's in every single term. So if we divide both sides by m, get rid of those. And so what I'm going to do is I'm going to move this term over. So we're going to have 7/10 times the final velocity of the bowling ball at the top of the ramp squared. That's going to be equal to, right, this term minus this term. So it's going to be 7/10, right, times the initial velocity or bowling ball squared minus the acceleration due to gravity, g, times our final height. And then I can multiply both sides by 10/7 to get rid of that. So this is going to give us that our final velocity of our bowling ball squared is going to be equal to the initial velocity of our bowling ball squared minus 10/7 times g times our final height. Right? And then if I take the square root of both sides, right, we get that the final velocity of our bowling ball at the top of the ramp is equal to the square root of our initial velocity, which is just 3.5 meters per second. I'm going to square that, minus 10/7 times g, which is 9.8 meters per second squared, times our final height of 0.76 meters, right? And this is all under the square root. There we go. When we punch this in, this gives us a final velocity at the top of the ramp of 1.27 meters per second. Right, we got there by using conservation of energy. So that's the answer to this problem. So the next problems we're going to solve are from the simple harmonic motion chapter. So these are the simple harmonic motion problems. Right. So this is going to be example 5. Example 5. And example 5 says, a person who weighs 670 newtons, a person who weighs 670 newtons steps onto a spring scale, steps onto a spring scale in the bathroom. I don't know why they added this in, but they did. Seems kind of unnecessary. And the spring compresses. And the spring compresses by 0.79 centimeters. So we're going to have to convert that to meters. So part A is asking, what is the spring constant? So what is the spring constant? And part B is asking, what is the weight? So what is the weight of another person? Who compresses the spring by 0.34 centimeters. Right. So part A is asking us to find the spring constant for this particular spring. And part B is saying, now that we know that, what weight does this other person have if they were to step on the scale? Right. Okay, so we have a free body diagram of our person standing on the scale. Right, this is the free body diagram of our scale. Right, there's the spring force pointing up, and there's the weight of the person pulling down. Right. So if we look at the sum of the forces in the y direction, right, the person has compressed this spring by stepping on the scale, but they're not like bouncing up and down on the scale, right? They're just stationary. So we want our acceleration to be 0. And looking at the forces in our problem, right, we have the spring force pointing up, and we have the weight pointing down. So we have the magnitude of the spring force pointing up, and we have the weight of the person pointing downwards, so it gets a minus sign. That's equal to 0. And so, right, if I add the weight to both sides, we get that the spring force is equal in magnitude to the weight of the person. But the spring force, the magnitude, is just K times the displacement magnitude. And then on the right-hand side, right, we have the weight of the person. But if I divide both sides by the magnitude for our compression, right, magnitude of our displacement, this gives us K, spring constant for our spring, is equal to the weight of the person divided by the magnitude of the displacement in the y direction. So the person had a weight of 670 newtons, right? And the displacement is 0.79 centimeters, but we need to convert that into meters. So we have 0.79 centimeters, right? But we know that in 1 meter, there's 100 centimeters. So we're doing the unit conversion we should have done earlier. Units of centimeters get canceled out, and we get a spring constant value of 848.1 times 10 to the power of 2 newtons per meter. right? Which is honestly kind of weird. Like, I don't know why they wrote it like this. In fact, I think it's less dumb to just write it like this. Right? I think it's about right. There we go. So this is the answer to part A, right? This is our spring constant for this particular scale. And now that we know that, let's try and solve part B. So part B says, what is the weight of another person who compresses the spring by 0.34 centimeters? Well, the free body diagram is going to be the same, right? So in order for this spring scale to be in equilibrium, right, we need the magnitude of the spring force to be equal to the magnitude of this person's weight, right? But we know that the magnitude of the spring force is K times the magnitude of the displacement. It's going to be equal to this person's weight. So we have this person's weight is going to be equal to K, which we found to be 848,100 newtons per meter, right? Times our displacement. And the problem says that our displacement for part B is 0.34 centimeters. So the person doesn't compress it as much. Centimeters, and we got to convert that into meters, but we know that 1 meter has 100 centimeters in it. Units of centimeters get canceled, and we're left with a weight. Right? We're left with a weight of 288.4 newtons. And that's our answer to part B. All right, so let's look at our last example for the day. So this last example is example 6. Example 6. So example 6 says that a small ball is attached to one end of a spring, that has an unstrained length, of 0.2 meters. Right, so this is the equilibrium length of the spring. Problem goes on to say that the spring is held by the other end. The spring is held by the other end. And the ball is whirled around in a horizontal circle. And the ball is whirled around in a horizontal circle at a speed of 3 meters per second. A speed of 3 meters per second, right? So this is our tangential velocity. So the spring remains nearly parallel to the ground. The spring remains nearly parallel to the ground. Right, during the motion. And is observed to stretch by 0.01 meters. Right, so 1 centimeter. So by how much would the spring stretch how much would the spring stretch if it were attached to the ceiling, if it were attached to the ceiling, and the ball allowed to hang straight down, motionless. And the ball allowed to hang straight down, motionless. That is a lot of writing. Okay. All right, so let's draw a picture to help us. All right. So we're swinging this ball above our head, right, in a circle. Let's say that this is the center of the circle. And let's say that, this is our spring, right? It's attached to a ball. And so this ball is just having a good old time being swung around at like 3 meters per second. 3 meters per second. And so the radius of this circle is the length of the equilibrium length of the spring, right? So 0.2 meters plus this additional stretched length. So it's going to be 0.21 meters, right? And so this is basically the problem we're working with. So this thing is going to be, in the first part of this problem, right? This ball is being spun around in uniform circular motion. So in this case, the thing that is providing the centripetal force required to keep this ball moving in a circle, right, is the force of this spring. But we know that the centripetal force is just the mass of the ball times the velocity of the ball squared divided by the radius of this circle. But we also know that the magnitude for our spring force, right, is just K times its, the magnitude of our displacement, X. So what we have is mv squared over r on one side, and on the other side, the magnitude for our spring force. So if we divide both sides by our displacement, I guess the magnitude of our displacement, we get that the spring constant for this spring is just mv squared over r times the magnitude of our displacement, x. Now at this point, we can't really do anything because, right, they haven't told us what the mass of the ball is. So at this point, this is kind of the best we can do for now. But this is where part 2 comes in. So part 2 says, now if we take this spring, right, with the ball on it, and we hang it from the ceiling. So now this is our ceiling. Take this spring, let it dangle down. We got this ball. And they're asking, right, how much would the spring stretch if we're actually attached to the ceiling and the ball were allowed to hang straight down motionless? So at this point, right, when it's hanging down, it's in equilibrium. It's not bouncing up or down, it's just sitting there. There's going to be 2 forces acting on this ball. There's the force of the spring, keeping it up. Then there's the force of gravity, right, the weight of the ball, pulling it down. And so looking at the free body diagram of this thing, we have that this sum of the forces in the y direction, we want them to be 0 because we want this thing to not be accelerating, right? So its acceleration is 0. And so the sum of the forces on the left-hand side, we have the magnitude of the spring force pointing up, which is why it's positive. And we have the weight mg pointing down, so that's negative. And that's all equal to 0. And so notice that, right, first I'm going to move the weight over to the other side. So we have the magnitude of the spring force is equal to the magnitude of the weight, right? But we know that the magnitude of the spring force is just k times this displacement. Maybe I'll call it y this time, right? Since now we're going the y direction. So that's going to be equal to mg, right? But we found out what k was, right? So k is just mv squared from the first part of a problem. So it's mv squared over r times our displacement x, right? And on the right, we have the weight of the ball. So we're just taking the result that we got from the first half of the problem, right? We're taking this k, and we're just plugging it in here for the second part of our problem. And so notice that the mass of the ball cancels out, right? And we're trying to find, I forgot to multiply by y, right? We're trying to find how far this thing hangs down or how far it gets stretched, right, when we just let it hang from the ceiling. So we're trying to find y in this problem. So what I'm going to do, I'm going to multiply both sides by r times x and divide both sides by v squared to give us the displacement y is equal to g times r times x, right, all divided by v squared. And it's at this point where we start plugging some stuff in. Right, so g is just 9.8 meters per second squared. R is the radius of the circle from the first part of the problem, but that's just 0.21 meters. X is the amount that this spring in the first part of the problem was stretched. But if you remember that we observed it to stretch by 1 centimeter or 0.01 meters. Right, so X here is just 0.01 meters. Now we're dividing by the speed of the ball as it went around the circle in the first part of the problem, but that was just 3 meters per second. So we're dividing by 3 meters per second squared. And if you punch all of this in, we get that the displacement in the y direction, right, if we just let this thing hang from the ceiling, it's going to be equal to 2.3 right, times 10 to the negative 3 meters. But this is equal to exactly equal to 2.3 millimeters. And that is the answer to our problem. And with that, we have finished the lecture.